now the comparison test. We have two series, a sub k's and b sub k's, and they're all positive terms. What we're going to be doing is there's going to be a series that we're interested in the convergence of. Let's say that we want to know, is the series of a sub k's convergent or divergent or not? Well, we're going to find a series of b sub k, something we are familiar with its convergence, and determine, based on its comparison to that series, if we can determine if the a's converge. So, what we want to do is, let's say we have a series of b's, and we know that term for term, the series of b's is larger than or equal to the series of a's. So, looking at each term, the b's are always bigger. And suppose that we know that the b's actually converge. Well, if the b's all converge, the sum of the b's converge, then the sum of the a's is going to converge. Or let's say that we know we have the series b's that we know is always smaller than the a's, but the series of b's diverges. Well, then the sum of the a's must also diverge. So, graphically, an illustration of that, let's say we're looking at the series of 1 over k squared. Well, we know that's a p series, p equal 2, we know it converges. Well, now let's say that we were looking at the series 1 over k squared plus 10. It looks very similar to this one, which we know this is convergent. So what can we say about that one? Well, how do they relate to each other? Well, I know that k squared is less than k squared plus 10. That's true for any k. Well, now I'm trying to compare 1 over k squared plus 10 to 1 over k squared. If you have an inequality and take the reciprocal of both sides, the inequality actually reverses. So what I've just shown is that this series, term for term, 1 over k squared plus 10 is actually smaller than 1 over k squared. Since these term for term are smaller than those, and these actually, when I add them all together, converge, then this one must converge. So that would be by the convergence test. This series also converges. Even though it's not a p series, it's similar to the p series enough where we can compare them and know that it's going to be smaller than the p series that does converge. Okay? This other example. I'm interested in 1 over the square root of k minus 3. That's not a p series, but I could compare it to the p series 1 over the square root of k. That's a p series where p is equal to 1/2. Which we know when the p series is, the p is less than or equal to 1, this one diverges. Well, the only way this is going to be helpful using the comparison test is if the 1 over the square root of k minus 3 is actually larger than that. Because if this one is always smaller, and when we add those up, it's infinite, then these would have to be infinite as well when we summed them. And if you look at the partial sums in the drawing here, you can see that the partial sums of this one are staying above the partial sums of this one, which we know already diverges. So it must diverge. Okay, now to establish this, though, we need to prove that 1 over the square root of k minus 3 is actually larger than 1 over the square root of k. So let's start with, we know, one thing we do know is we know that k is bigger than k minus 3. And so that means the square root of k would be actually bigger than the square root of k minus 3. And now I want fractions, though, so let's take the reciprocal. 1 over the square root of k will be smaller than 1 over the square root of k minus 3. So term for term, this one's actually the smaller terms. So when I try to sum them, square root of 1 over square root of k must, well, it's going to be less than or equal to, obviously, these. Since term for term, they were always smaller. But this one diverges. And this one's larger, so it has to diverge. So that's the idea behind the comparison test. The difficult thing about the comparison test is that you've got to establish this inequality. You've got to actually show that this A sub k is less than or equal to B sub k, or vice versa. And the only times that I find this real easy to use is when maybe you have a numerator that's just a constant, and then it's easy to manipulate it. Now, had this first one actually been a k squared minus 10, we couldn't have established the identity, the inequality that we needed. So let's look at some problems. Okay, I want to see if these converge or not. They're more complicated, so I want to see if I can compare them to something maybe that is something I'm more familiar with. Okay, so now to compare this one, well, I said I wanted to use it only when the numerators were constants, and these aren't constant numerators. Well, let's try to build this up. If I'm trying to compare this to something, I could just ignore the minus 1 on the bottom. It's really kind of insignificant as k gets bigger and bigger. And so this resembles 1 over 2k. So I'm just kind of ignoring the minus 1 to get a feel for what I'm expecting here. 1 over 2k, I don't have to worry about the 1/2. The 1 over k is actually the harmonic series, and I know that one diverges. So there's a good chance this one's going to diverge. It looks close to the 1 over k. So let's check. First off, what I do know is I know 2 to the k to the 4th minus 1 is smaller than 2k to the 4th. Okay, so that tells me that 1 over 2k to the 4th minus 1 is going to be bigger than 1 over 2 to the k, 2k to the 4th, just by taking the reciprocals of both sides and switching the inequality. Now, I'm trying to construct this. Well, I lost my 2 somewhere. So to get that, in this inequality, I'm going to multiply both sides by k to the 3rd. Now, k to the 3rd is positive. So when I multiply both sides by k to the 3rd, I get k to the 3rd over 2k to the 4th minus 1, and that's bigger than k to the 3rd over 2k to the 4th, okay, which is equal to 1 over 2k. Now, don't let the 1/2 of the 1 over k bother you, because if the sum of 1 over k's diverges, a number of times it is going to diverge as well. Taking half of something that's going to infinity is still going to go to infinity. So we can treat this as it's the harmonic series. So the series 1 over 2 to the k diverges, since that is just 1/2 times the p series with p equal 1. So I would note that it's the p series p equal 1 that justifies that. And this one is always bigger than that one. So I've established my inequality that this one is bigger than something that we already know diverges. So by the comparison test, k to the 3rd over 2k to the 4th minus 1 must also diverge. Okay? So note the series that you're using and its convergence, and then you've got to state the inequality, the way that you're doing it, and what conclusion you get from the comparison test. Okay, the second one here, got a natural log of k. I need to somehow compare that to something I know. So what I'm going to start with is the fact that I know, kind of like you know sine is always between -1 and 1. Something else that I always know is natural log of k is always less than k. Okay, so that's always going to be true. So if I start with that inequality, and then I'm going to go ahead and divide both sides by k cubed, that means that natural log of k over k cubed is less than k over k cubed. I can multiply both sides by the same positive number without affecting my inequality. So I chose 1 over k cubed to multiply by. Now this k over k cubed is just 1 over k squared. So what I've just established is that this term is less than a term of this series, 1 over k squared. And I know that the series 1 over k squared, which is a p series, p equal 2, converges. So that means that since this one is always smaller than this one, and this one converges by the comparison test, natural log of k over k cubed must also converge. So you must establish your inequality, state the series that you're comparing it to, what you know about its convergence or divergence, and give justification, and then state what the comparison test actually tells you based on the inequality you set up, and if you had the right convergence or divergence of the one you compared it to. Okay? So the key to using the comparison test is making sure you can find the right comparison series, because if I found that one was smaller, something smaller that converges doesn't mean the larger one converges. It's only if the smaller one diverges that the bigger one's going to diverge, and only if the bigger one converges that the smaller one converges. So you have to have your inequality set correctly for the type of convergence that you're going to be establishing. This is the comparison test.